Swayam Prabha. Digital India. Educated India.
Good morning. This is our last lecture on the topic of function approximations. In the previous lecture, we saw several ways of function approximation by the use of several families of eigenfunctions of different Sturm-Liouville problems, and in particular we also went through the Fourier series, which provides some additional facility other than what any family of eigenfunctions of a Sturm-Liouville problem would offer. Towards the end, we also discussed how to extend the idea of Fourier series to a function which is not periodic, which is defined over the entire real line, and it is a non-periodic function. For that, we asked this question: how to apply the idea of Fourier series to a non-periodic function over an infinite domain. So, for that we constructed the Fourier series over a finite interval of length 2l, and then we let the variable L increase and tend to infinity, and as a result we arrived at this representation of the function, which is the Fourier integral. Now, in the Fourier integral, this is the coefficient available in the form of an integral, and similarly this integral over an infinite domain of the continuous variable v. So, these two integrals are the coefficients, and the Fourier integral representation turns out to be a superposition of infinite such components with continuously changing value of p. Now, in the case of the Fourier series, this integral was a summation. Now, here the summation becomes a sum of continuous components, and therefore, you get an integral, and in the place of the two Fourier coefficients we have got these in a similar manner in which as we got it in the case of Fourier series. So, this Fourier integral can be now represented as this integral with the coefficients as coefficient functions. Earlier these coefficients in the case of Fourier series were a n and b n, that is, they were indexed. Now, these are continuous functions, not for n equal to 1, 2, 3, 4 and so on, but p which varies continuously from 0 to infinity. So, in place of Fourier coefficients indexed with an integer variable n, we have got Fourier coefficients which turn out to be continuous functions of the frequency variable p, and these are in a way the corresponding amplitude functions ap and bp, which are these two integrals. So, the only difference here is that this is an integral rather than a sum of terms for large number of n's, and the coefficients are defined not for different values of n, but for continuous variable frequency variable, which is p. Now, using this itself, you can also represent this large double integral in a somewhat different manner, in which you can push cos px inside this integral and sin px inside this integral, and then you get this form of the Fourier integral expression, which is called the phase angle form, in which you find that cos px cos pv plus sin px sin pv is replaced with this, and this turns out to become a straightforward double integral. Now, from this double integral, with a little more work, we can define a an integral transform, and how it is done is here. So, in this cosine we can replace in this manner, cos theta is e to the power I theta plus e to the power minus I theta by 2. So, if we substitute this expression for the cosine term there, then that by 2 comes here, and inside we have got e to the power I p x minus v plus e to the power minus I p x minus v. And then we find here that in this double integral dv, for that differential the corresponding variable v varies from minus infinity to plus infinity, and this frequency variable p varies from 0 to infinity. Now, this term in the integrand can be omitted if we consider this limit also from minus infinity to infinity. That gives us a more symmetric representation. To see that, what we do is that we can substitute p equal to minus q. So, that means that for this integral, if we try to separately evaluate this component, then in place of minus p we will have q here, in place of dp we will have minus dq, and therefore, the limit of this integral over p will become from 0 to infinity. Because of the sign change, it will become minus infinity to 0. That is, first of all it will become 0 to minus infinity, and then because of the sign change we will have the limit reversed. So, now if we recognize this, that the integral of this term f v into this turns out to be actually the integral of the same thing over minus infinity to 0, then the addition of these two terms is the addition of an integral from minus infinity to 0 and then from 0 to infinity. That means, this integral and this integral together will give the complete integral from minus infinity to plus infinity, and that gives us the complex form of the Fourier integral, in which it is a single exponential function here with f v, and we have this double integral. And then in the complex form of the Fourier integral, this term also, rather than cosine and sine, has become this exponential function with imaginary index, and this Cp, the amplitude function, has become the integral that you get when you take only f v into e to the power minus I p v, and plus I p x remains here, right. So, from the original Fourier integral also we got similar a p and b p. Now, in a complex form, the two coefficients combine together to give us the complex coefficient function. Okay. Now, this actually holds the root of the definition of the Fourier transform. Let us see that directly here. In this chapter, we will not go into a great detail, but we will just see how the integral transform called Fourier transform gets defined from the complex form of the Fourier integral. So, with a different notation here, in place of x we have got t here, in place of p the frequency variable we have got w here, and so on. Otherwise, it is the same expression, and the 1 by 2 pi, that factor has been split into two parts. One is here, 1 by root over 2 pi, and the other is here. Now, here this is the same earlier complex coefficient function, and but with this factor here rather than the earlier factor that we had. Now, this can be considered as the function representation in which we are talking about a composition, that is addition, the sum of an infinite number of functions, which are these, in the form e to the power minus w t by root over 2 pi, that is e to the power minus w t divided by root over 2 pi, and the coefficients of these superposition, turns out to be this, that is the amplitude function. Okay. And the amplitude function varies continuously with the frequency. Now, this function representation is in a way the linear combination, the composition of a large number of frequency components the frequency components are here and the corresponding coefficients are here, corresponding amplitudes are here, and this amplitude turns out to be a function of the frequency that you get from here. So, this function of frequency which turns out to be the amplitude is the Fourier transform. So, amplitude of a frequency component, that is this bracketed term here, and that is the Fourier transform, and this is a function of the frequency variable. So, that means a waveform has large number of components of continuous frequencies, and now for every frequency this gives us the amplitude value, and when with this amplitude value and this frequency we construct the term that component completely, we have got this, and such terms infinite in number distributed continuously over the frequency variable is the complete function. Now, if we rather have this Fourier transform in our hand, then that Fourier transform sitting here with e to the power IWT multiplied and dW put here and integrated like this, that is in this entire place, if we put this Fourier transform, then we have got this, and this integral will recover the original function, that is the inverse Fourier transform. The way we defined earlier Laplace transform and inverse Laplace transform, in a similar manner we have got these Fourier transform and inverse Fourier transform. Fourier transform and inverse Fourier transform, these are quite symmetric in their look. Here you have got e to the power minus IWT to be multiplied and then integrated, here you have e to the power IWT multiplied and then integrated. So, this gives you very similar expressions for evaluating the Fourier transform and the inverse Fourier transform. Now, these transforms are extremely useful in the solution of differential equations, partial differential equations, and also in the field of signal processing. We will not go into the detail of that because the main agenda of this lecture is another kind of function approximation in which the objective is different than all the function approximation techniques that we have discussed till now. Earlier, when we were discussing the interpolatory approximation of functions, in that context we discussed three criteria of approximation of functions. One was interpolatory approximation, which we studied in that particular lesson, and the other was least square approximation, which we have studied in several sections in this course. First, the linear least square problem, which we studied in the module of linear algebra, and then we studied the nonlinear least square problem, which we studied in the context of nonlinear optimization, and finally the same least square approximation we have been discussing till recently, which are least square approximation based on the error value developed through integrals rather than sums of finite number of components, finite number of error values. So, that least square approximation we have studied already. Now, the third criteria of approximation of a function is a minimax approximation, in which the objective is not the sum of square all over the domain, sum of squares of errors all over the domain, but the objective function to be minimized is the maximum error. So, therefore, this kind of an approximation is called minimax approximation, and one particular family of eigenfunctions, that is the solutions of the Chebyshev equation and called the Chebyshev polynomials, give us specific interesting properties which are directly useful in the case of minimax approximation, and therefore, this topic of minimax approximation we start with a discussion of Chebyshev polynomials. This differential equation resembles the Legendre equation to a great extent. In the case of Legendre equation, we had a 2 here, okay, minus 2. Here we have got minus 1. Now, in place of this minus 1, if we had minus 2, then we found that this minus 2x turned out to be exact derivative of this, and therefore, these two terms together in the case of Legendre equation turned out to be the perfect differential coefficient of 1 minus x square into y prime. Now, in this case that 2 is missing, so it will, this much right now is not in the self adjoint form, right now not in the Sturm Liouville form. So, if you can, if you divide the entire equation with this square root of 1 minus x square, then you will find that here then you will have square root of 1 minus x square, and here you will have minus x by square root of 1 minus x square, and in that case the terms together will be in the self adjoint form, and together they will give us the derivative of this combined term, and through the division here you will get this. Now, there is one interesting point here, that if we change the independent variable here and make this substitution x equal to cos theta, then this differential equation quite easily boils down to this differential equation is the same differential equation which we saw in the case of Fourier series. Now, from here we can very easily see that the solutions of this will be cosine nx and sin nx. They will be the linearly independent solutions of this differential equation. Now, in particular, the solution sin nx will be very complicated functions, but the other family of solutions cosine nx, that is for different values of n, cos 0, that is 1, then cos x, sorry, not x but theta. So, the solutions of this will be cosine theta and sin theta. So, the term sin theta, when finally expressed in terms of x back by putting theta equal to cos inverse x, will turn out to be quite complicated functions. On the other hand, the other solution, that is y equal to cos theta, will turn out to be polynomials in x. So, you can see that. So, that is why we are particularly interested in the polynomial solutions of this differential equation, and note that this differential equation also will define a singular Sturm Liouville problem, just like the Legendre equation, because here the function Rx which appears here is 0 at x equal to minus 1 and at x equal to 1. That means you do not need any boundary conditions to define the Sturm Liouville problem. So, this differential equation will define a singular Sturm Liouville problem over this interval. Legendre equation also did the same thing. Now, we are particularly interested in the polynomial solutions of this particular Sturm Liouville problem, and one family of solutions of that will turn out to be polynomial solutions. Now, the way we discovered this fact in the case of Legendre polynomials, it is possible to discover the same fact for Chebyshev polynomials also in the same manner by consideration of the series solution, and noting that for integer values of n, the series terminates and gets you polynomial equations, polynomial functions. The same conclusion will be reached through this arrangement, in which we replace x with cos theta, and solutions of this turn out to be cosine n theta, sin n theta. We discard that sin n theta because that is not going to give us polynomial solutions, but cosine n theta will give us polynomial solutions, and for all values of n, cosine n theta will have a value 1 when we take x as 1. So, the closed form expression for that particular family of solutions which are going to turn out to be polynomial solutions is this, that is T n x is cosine n theta, theta is cos inverse x. Now, if we put n equal to 0, then we get T 0, which is cos 0, that is 1. If we put n equal to 1, then we get cos inverse x, which is x. If we put n equal to 2, then we have got cos 2 theta. We know that cos 2 theta is twice cos square theta minus 1. Similarly, cos 3 theta will be 4 cos cube theta minus 3 cos theta, and so on. Okay. So, we can also very easily prove that the family, this family of functions T0, T1, T2, T3, etc. will satisfy this 3 term recurrence relation, that is Tk plus 1 will be twice x Tk minus Tk minus 1, which means that after evaluating the two of them, we can evaluate others in terms of polynomials directly rather than writing multiple angle formulas of cosines from this recurrence relation. What other properties these polynomials have, these solutions of the Sturm-Liouville problem have? Now, that with a little exercise, we can establish a lot of properties of these polynomials. In the exercises of chapter 39 and chapter 40 of the textbook, we have the steps to establish many of these properties. So, it is expected that the student will go through those exercises and execute those steps to learn the derivation of these properties first hand. Here we will just summarize the immediate observations, immediate properties for proceeding further. Coefficients in a Chebyshev polynomials are all integers, which is different from the Legendre polynomials. In particular, the leading coefficient of Tn will be 2 to the power n minus 1. For even n, that is for T2, T4, T6, Tnx is an even function, because they will have only the even powers, while for odd n it is an odd function. This is the same as the Legendre polynomials. In the case of Legendre polynomials also, we noticed this property. All the Chebyshev polynomials will have the value 1 at x equal to 1. That is obvious, because at x equal to 1, cos inverse x will be 0. So, for all values of n into 0 is 0. So, cos of 0 will be 1. So, value of all these polynomials for x equal to 1 will turn out to be 1. That means, all of them are bunched at 1. Then we find that at minus 1, the value will turn out to be this, minus 1 or 1, depending upon whether n is odd or even. This also is same as Legendre polynomials. Legendre polynomials, that family also had this property. Okay. And this is a very interesting property, that is the value, the absolute value of Tnx over this interval is always less than or equal to 1. This also is there in the case of Legendre polynomials. Again, zeros also, the distribution of zeros of a Chebyshev polynomial also shares a similarity with Legendre polynomials. The zeros of the Chebyshev polynomial are all real and lie within this interval. Okay. But the locations of the zeros of Chebyshev polynomials turn out to have very particular significance. They are at these locations, and these locations are called Chebyshev accuracy points. Why? That we will explore further. Further, another interesting thing is that the zeros are interlaced by the zeros of Tn, the nth Chebyshev polynomial are interlaced by those of Tn plus 1. That means, the nth degree Chebyshev polynomial will have n zeros, and every zero of the Tn function will turn out to be enclosed by 2 consecutive zeros of the next order Chebyshev polynomial. This interlacing property is also interesting. Now, we find that these 3 properties, except this part, the Chebyshev polynomials share with the Legendre polynomials, and this next property, extrema of Chebyshev polynomials, have a very unique property which no other family of functions possesses, and that is all extrema of the Chebyshev polynomial Tn are of equal magnitude. Magnitude is unity, and they alternate in sign and occur at these values of x. One maximum, next minimum, next maximum, next minimum, all these maxima and minima of the same absolute value 1. That is, maximum value 1, then minimum value minus 1, then maximum value 1, minimum value minus 1, maximum value 1, minimum value minus 1, and so on. So, this is a very unique property, and this property is called the minimax property. We will see the significance of this property. Orthogonality and norms. So, this is the integral here is equal to 0 for m not equal to n, that is the outcome of the result on the Sturm-Liouville problem. Here you see that the function Px is 1 by root over 1 minus x square. So, that is why two distinct solutions, that is two solutions of this Sturm-Liouville problem corresponding to different values of n, that is different eigenvalues, distinct eigenvalues, will turn out to be orthogonal with respect to the weight function 1 by root over 1 minus x square. So, the statement of orthogonality of Chebyshev polynomials turns out to be like this. So, this is the statement on orthogonality, and the definition of norms will come when we put m equal to n, and for m equal to n which is not 0, we get it pi by 2, and for m equal to n which is 0, we get pi. This is similar to what we found in the case of the Fourier coefficients. Now, with these properties, we can have a close look at one such sample Chebyshev polynomial between -1 and 1. So, between -1 and 1, the Chebyshev polynomial varies like this. You see, the zeros and extrema of this turn out to have a uniform distribution over the theta variable. Say for theta equal to 0, x is 1. Okay. So, the value of Chebyshev polynomial is 1. Then for theta equal to 30 degree, pi by 6, x is here, cos 30 degree, that is root 3 by 2. Okay. So, at that we have got a 0 of the Chebyshev polynomial. So, then 0, 30 degree, then 60 degree. At theta equal to 60 degree, we have got this negative value -1. So, here was one extremum value, maximum, next minimum. So, at 30 degree, at 0 we had maximum value, at 30 degree we had a 0, at 60 degree we have the minimum value -1, then at 90 degree x equal to 0, we have got T3x also 0. So, that is a second 0 from this side. Then again at 120 degree we have got the maximum value, at 150 degree we have got a 0, at 180 degree we have got this extremum value. So, the zeros and extrema are distributed like this. The extremum values have the same absolute value 1. These maxima are at value 1, these minima at value -1. This is a distinct property which is not shared by any other family of functions, and as you compare it with say Legendre polynomials, you will find that this is the graph of the 8th order Legendre polynomial and 8th order Chebyshev polynomial superimposed. So, this is the graph of P8 Legendre polynomial, and this is the graph of the Chebyshev polynomial. You can see that the Chebyshev polynomial has this equal ripple property, that is equal amplitude oscillations. So, from here it goes all the way down. In the case of Legendre polynomials, as you proceed towards the center of the domain near 0, the amplitude tends to come down, compared to here it comes down towards the center. In the case of Chebyshev polynomials, every extremum is at the extreme value of -1 or 1. So, 8th order polynomial, it has got going down, going up, going down, like 8 such trends you have. Okay. And all the zeros you can see here 1, 2, 3, 4, 5, 6, 7, 8, and they are distributed uniformly over the theta variable cos inverse x. So, being cosines and polynomials at the same time, Chebyshev polynomials possess a wide set of interesting properties which have this unique application in Minimax approximation. The most striking property is this equal ripple oscillations leading to the Minimax property. We will see this in two stages. First, what is this Minimax property of Chebyshev polynomials? The important result is that among all polynomials p n x of degree n with the leading coefficient equal to unity. Why this is needed? Because if we want to compare two polynomials, then we can make no comparison if one of the polynomials can be multiplied by an arbitrary number. So, we need to fix something for both the polynomials to make a worthwhile comparison. So, we say that we will fix the coefficient of the largest degree term, that is we are talking about monic polynomials. So, the leading coefficient will have unity, that means x to the power n plus a1 x to the power n minus 1 plus a2 into x to the power n minus 2 and so on. So, the leading coefficient is 1. So, among all such polynomials of degree n with the leading coefficient unity, that is among all monic polynomials of degree n, this is the one which has the least deviation from 0. Now, why this factor? Because we already know that Tnx has the leading coefficient which is 2 to the power n minus 1. So, to make it monic, we must multiply it with 2 to the power 1 minus n. Okay. So, the or divide with 2 to the power n minus 1. So, therefore, the monic version of the nth order Chebyshev polynomial is this, and among all monic polynomials of nth degree, the claim is that this one will have least deviation from 0 over this interval. Okay. So, mathematically we can say that maximum over this domain, this interval of absolute value of p n x is always greater than equal to the corresponding value for this particular function. So, all other polynomials will deviate more from 0 and this will deviate least, and that least deviation turns out to be this. Now, this equality part is easy to establish because we already know that Tnx will deviate between minus 1 and 1. Okay. That means the absolute value of the deviation of Tnx is 1. So, absolute value of the deviation of this factor into Tnx will be this factor itself. This unit equality part is quite obvious. For the inequality, that is all other polynomials will deviate more, we need to do something. So, for that we first assume that suppose there is some other polynomial other than this which has even less deviation. So, if there exists some monic polynomial p n x of degree n which deviates less, okay, which deviates less than this. If we assume that like that, then what we can do is that we consider the values of this candidate polynomial at the extrema of the Chebyshev polynomials. Now, already know that the nth degree Chebyshev polynomial has n plus 1 alternate extrema, positive, negative and so on. So, each with this absolute value that we already know. So, at those extremum points of the Chebyshev polynomial, we consider the values of this. Now, these points are giving us the maximum deviation of this, okay, which is 2 to the power 1 minus n, and we know we have assumed that this candidate function deviates less. So, if it deviates less, then it will never be able to cross the extremum value of this. Okay. So, that means that if we consider this difference, then this part in the difference will always dictate the sign of the difference polynomial q n x, right. So, if this is positive, then whatever be the value of this, the difference will be positive. If this is negative, then whatever be the value of p n, the difference will be negative, because this fellow's value has been assumed to be less than the extremum value of this, and we are evaluating at the extremum points. Okay. Then this difference polynomial will have the same sign as the first part. Now, we already know the nature of the signs of this in the sequence, that is n plus 1 locations, n plus 1 alternating extrema this function has. So, its sign will be alternating at these n plus 1 locations, positive, negative and like that. Okay. So, with alternating signs at n plus 1 locations in sequence, t n x and therefore q n x also will have n intervening zeros. So, because this q n x has the same alternation of sign as this, because this one is going to dictate the sign of q n. So, q n with alternating signs at n plus 1 locations will have n intervening zeros, positive here, negative here. So, in between q n x must have a 0. So, between n plus 1 extrema of alternating sign, it will not extrema of this difference function, but with alternating signs at n plus 1 locations in sequence, it will have n intervening zeros. But then that is something very awkward, because both of these were monic polynomials, which means that in both of these cases the coefficient of x n was unity, and in that case in the difference the x n term will get cancelled, and this polynomial is actually an n minus 1 degree polynomial, but then we have just now found that it has n intervening zeros. How can an n minus 1 degree polynomial have n zeros? So, this leads to a contradiction, which means that this assumption of a monic polynomial of less variation, less deviation is certainly wrong. So, through contradiction we get this result that among all polynomials of degree n, it is the Chebyshev polynomial, the scaled version of it to make it a monic polynomial, deviates least, and this turns out to be the deviation. Now, how do we utilize this property? Let us explore. With a linear combination of the Chebyshev polynomials, we will have this series, which is called the Chebyshev series, for which we can construct the coefficients a0, a1, a2, a3, etc., as we have earlier studied. That is how to construct the generalized Fourier coefficients for this Chebyshev series. There are the Chebyshev coefficients for which we have these expressions. Now, typically we would not be able to construct this infinite series. So, we typically try to represent a function with a truncated series only up to a finite